All right, so this is our second set of notes in our circles unit. Here we're looking at circles, angles, and arcs. In the last one we talked about segments and lines. Now we're getting more into the curves of the circle itself. All right, so we have four definitions that we're looking at here to start off with, and these definitions will carry us through the rest of this set of notes as well as through the rest of the chapter. The first of which is a central angle. And we already know what an angle is. It's two rays that have a common vertex. That vertex, of course, is what we refer to as the corner, so to speak, of the angle. It's that point here. So an angle whose vertex is the center of a circle is called a central angle. So in this case, if we look at angle BPC, its vertex is the center of that circle. And remember in the last set of notes, we talked about how the center will be marked with a point to indicate it is the circle. So whenever we name an angle, and this should be review, we use the little angle symbol, and then we write the 3 points corresponding to 3 points on the angle as if you're tracing the angle with your finger. So here B to P to C would be one variation, or I could go in the opposite order from C to P, and then to B. So in this case, B, P, C is one possibility. Reverse order would also be correct, but the P, that vertex, that point has to be in the middle. All right, when we talk about the measure of an angle, and here again, this should be review, remember that we take the name and we put a little m in front of it. So the measure of that angle would be denoted by the measure of angle BPC. And there again, that notation should not be new. All right, one thing that we do need to add in terms of these arcs, arcs are parts of a circle. So we have minor arcs, a part of a circle that measures less than 180 degrees. Major arcs, a part of a circle that measures between 180 and 360 degrees. And then we have semicircular arcs, an arc whose endpoints are the endpoints of a diameter. Now when we're talking about measuring an arc, it's going to come back to the measurement of the angle, and we'll talk about that in just a second. All right, so a minor arc, part of a circle that measures less than 180 degrees. So we know in terms of a circle, there are 360 degrees possible. 180 degrees, of course, would be half of that. So here we can clearly see that this angle, BPC, has a measure that's less than 180 degrees. So for that reason, the arc that connects points B and C is the portion of the circle inside that angle. Here, this arc is what we would refer to as a minor arc. Corresponds to a circle, or an angle rather, whose measure is less than 180 degrees. When we name an arc, you name it with the two endpoints. When it's minor, name it with the two endpoints, B and C. And we have several different objects that we name with two letters. We have segments that we would draw a little segment bar across the top. If it were a line, we'd draw a little line across the top. If it were a ray, we'd draw a little ray across the top. To indicate that this is a curved portion of a circle, that it's an arc, we draw it as such. We draw a little curve above the two letters. And that's what indicates to me that it is an arc, first of all, connecting points B and C. And because there are only two letters there, I can tell that this is a minor arc, meaning its measure is less than 180 degrees. When we talk about the measure of an arc, it's the same type of notation that we use for an angle. We put a little m in front of it. So the measure of arc BC would be little m and then the name. Now one thing to note, the measure of an arc and the measure of the central angle are going to be equal to each other. So in this case, the measure of this angle BPC is the measure of that arc BC. All right, let's look at a major arc, a part of a circle that measures between 180 degrees and 360 degrees. So in this case, the major arc that we have would go from point B all the way around in the other direction to point C. So to indicate that I'm going in the opposite direction, not into the angle, but rather outside of the angle, we have to include another letter. And the other letter that you use is any other point that you're passing through to get from point B to point C. In this case, I passed through point A. So one way to name this particular major arc measure being more than 180 degrees, is to write BAC. In other words, I'm starting at point B, I'm ending at point C, but I'm passing through point A along the way. There again, to indicate it's an arc, we're going to draw a little arc above all three letters. In terms of its measure, the same notation gets used, the measure of arc BAC. And there again, the measure of that arc is equal to the measure of whatever this angle would be outside of, in the exterior of angle BPC. So for example, if I say that this angle has a measure of, let's just make it easy, 90 degrees, then the other 270 degrees would be here, outside of that angle, which means the measure of this minor arc is 90 degrees. The measure of this major arc would be 270 degrees. Now, keep in mind, these two measures totaled 360 because there are only two arcs in this diagram. If there were more than two arcs, then that wouldn't necessarily be the case. We'll talk about some examples of that a little bit later. All right, so let's look at a semicircle. A semicircle is an arc whose endpoints are the endpoints of a diameter of a circle. So let's draw a diameter in, and I'm going to do that by extending the segment from B to P. I'm going to take my straight edge here, and I want to draw myself a diameter. Now, I intentionally left the diameter off of this diagram initially because I wanted us to be able to talk about the diagram without that letter there. All right, and we are going to, let's just kind of continue our trend. We're going to name this point down here D. So we have a diameter BD, that's segment. There are two semicircles formed. We have the semicircle from B to A to D, and we have the semicircle from B to C to D. Either of those would be fine. It doesn't matter which one you use. So in this case, one possible way to name that would be from B to A to D, the arc above it, or we could do BCD with the arc above it. There again, measure is still the name of the arc with the little m in front of it, just like it is for an angle. And that takes care of how we talk about names of objects versus talking about their measures. When we talk about the measures, we're going to be talking in degrees like we do with angles. When we're talking about their names, it's just referencing the object itself. All right, so we have three definitions and theorems down here at the bottom of the page that we want to look at as well. The first of which is the arc addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. Now remember, adjacent, we've talked about before with angles. Adjacent means neighboring. They share something in common, but they don't overlap otherwise. All right, so in this case, we have a couple of arcs we can look at. We have an arc from D to E, and I can see there again visibly that that is less than 180 degrees in this particular case, so I'm going to name that like I would a minor arc. And I have an arc from E to F. I'm going to use that in a different color. So what this theorem is saying, or what this postulate is saying, is that if I were to take the measure of arc DE, remember how we indicate the measure there, that's going to be some number in degrees, and I add to it the measure of arc EF. Grab my green marker here. So if I take these two smaller arcs and I add them together, and I can go ahead and add them because they are adjacent. They touch each other, they intersect at point E, but they don't overlap at all. There are no parts in my diagram that are both pink and green. So the overlap, or the only intersection between them, is that point, and that's what makes them adjacent. So the measure of an arc formed by two adjacent arcs, meaning what if I add these together? What's that going to do? Well, that's going to take me from D all the way past point E, or through point E, to point F. Now, in this case, that appears it might be a semicircle, but I'm really not sure if it is, so I'm not going to assume that it is. But what this is saying is if I were to take these two arc values, these two measures, and add them together, then their sum would have to be equal to the measure of that larger arc that they together form. So the measure of arc DE some value of degrees, number of degrees, plus the measure of arc EF is going to be equal to the measure of arc DF. And that's kind of basic common sense, I like to think, but if not, got our postulate that's telling us so. All right, congruent arcs. We've talked about congruent circles in the last set of notes. Here we're looking at congruent arcs. Two arcs of the same circle or of congruent circles that have the same measure. So in terms of our circles, let's draw two circles that are the same size, or at least approximately the same size. We want them to, we're pretending that they're the same size. So I've got two circles here that I am going to say are congruent to each other. So here we're looking at two congruent circles. I need two arcs that have the same measure. So let's say on this first one that we draw a point here, we'll call that A, and a point there, call that B. So the arc in this case from A to B would be right here along the circle. Likewise, in the other one, I'm going to draw an arc that's the same size. So I'm going to draw a point C, and then same size arc, point D. So these two arcs are congruent to each other if they have the same measure. So if arc AB is congruent to arc CD, if that's true, then their measures are equal. So the measure of arc AB is equal to the measure of arc CD. So if one of them is a 60-degree arc, then the other one's a 60-degree arc. They have the same measure. And then the last bit of vocab that we have in this case, in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in the same circle or in a pair of congruent circles. We'll look at a same circle in this case. We looked at congruent circles on that one. So we're going to draw a single circle over here. Ooh, that's not a very pretty circle, but we can pretend. And I'm going to add a couple of chords. In this case, we're talking about corresponding chords. And I want these two chords to appear to be the same size. So I'm going to draw them as close to the same length as possible. Remember, a chord from our last set of notes is a segment that connects 2 points on the circle. So I'm using A and B there. We'll use C and D on this one. And there again, I've got two chords that are the same length. So what this is saying in this theorem, if those two chords are congruent, if segment AB is congruent to segment CD, if the chords are congruent, then the arcs must also be congruent. Then arc AB must be congruent to arc CD. So this measure will be equal to that measure. Now keep in mind with the segments, the measures to determine if they're congruent are measured in units of length, like inches, feet, yards, miles, etc. Centimeters, millimeters, whatever. When we're talking about arcs, we're talking about their measures being in degrees. So if these two segments have the same length, then the number of degrees in each of these arcs would have to be the same as well. Now this theorem is an if and only if, which means if I were given that the arcs are congruent, so if arc AB is congruent to arc CD, then I can conclude that the segments must be congruent. So this does work bidirectionally. It is an if and only if statement, which means one of these two things is going to be given, either the congruent segments or the congruent arcs. The other will be your conclusion. Okay, so that takes care of the vocab that we need to talk about. On the reverse side of your notes, we're going to look at some examples. So let's take care of that next.